Thermal conductivities of elements and materials. I did a video a while ago on, effectively in 2006 or so, technology hit a limit with silicon-based processors. We're running into a limit where, on a mechanical level, making them smaller, which used to make it take less energy to do the same amount of work, so we could get away with running them faster and have the same energy budget per square inch or whatever. That failed, and it's given somebody's name, and that's it's like the such and such principle. But we're at the point where we need to either scale up by having larger numbers of chips, basically making computers bigger and bigger until we end up with buildings filled with them, which is already going on, by the way. Look at Google. Or make them more efficient. But we also are at another impasse. Recycler society and culture. Durability society. Which one do you choose? In the 1940s and 50s, a lot of people have a it ought to be the way it used to be in the old days attitude, where things lasted. I will tell you personally, I can go out in the garage that's 50 feet away from me, against that wall in that box that I open up with a lock on it, and I can find a drill that was made in the 1940s that will probably work in another 100 years, period, full stop. The damn thing doesn't break. Yes, it's older technology, and it's less efficient by 5% than a brand new one that's supposed to be high efficiency. We didn't perfect drills, but we pretty much did if they run on electricity and use copper wire. Just like wire and other materials has efficiency ratings for electricity, there's also requirements that we talk about the efficiency for heat. The only other way to speed up computer chips, even though it's going to waste more energy and use more energy, is to produce less damage by that waste heat being removed. Now, if you haven't noticed it, you don't keep your ice cream cool on a hot day by sticking a heat sink on it and hoping that'll work. That's done by heat pumping. That's kind of cheating, isn't it? And again, our technological abilities hit a limit. We can make food happen that you can store forever by doing really clean environment, really well sealed. Cook it first before you put it in the can, or cook it in the can, as they say with beef stew. Dintimore. But eventually you're going to hit an upper limit where there's a certain maximum shelf life. 100 years with wet food in a can, ask any cat, is pretty damn good. But we have a limit. So what's the factors controlling heating and cooling in a computer? How much heat sink? You might have heard that word. Heat conductivity seems like a pretty obvious thing to bring up. Normal people can talk about it. Also, a heat battery or thermal mass. Some of you who do buildings know what thermal mass kind of refers to, so let's talk about it. Thermal mass is like a battery. Thermal conductivity is like the wires from it. So let's talk thermal conductivity. I know that's not correct. Some of you are correcting me already, caps locking it, but let's continue. Thermal conductivity of materials. We're going to use a unit based on Kelvin, which is a temperature measurement, not any different than Fahrenheit or Celsius. And 300 Kelvin is around 80 degrees Fahrenheit. We're going to do everything based on under 300 degrees Kelvin or 80 degrees Fahrenheit, about body temperature down to room temperature. That's because most of these are referencing that temperature or that range, so we're going to use those as the basis. There's going to be variation here. Also realize, depending on what you're talking about, the material you're talking about, as far as conducting heat, it will change when it gets warm, because heat affects material a lot or little, depending on what it is. How conductive is water? Now, water can be poured over something cold. It conducts heat out temporarily, absorbs it as a thermal mass or battery or whatever you want to call it, and then as it's flowing, it pulls it away. Refrigerators use a similar but not identical thing. We're going to get to that in a minute. What's the thermal conductivity of water? Well, it changes with temperature, but at room temperature, body temperature, in that range, 80 degrees Fahrenheit or 300 Kelvin, around thereabouts, we get half a unit. It's 0.6 watt meter Kelvin. I'm not doing it correctly because it doesn't matter. We're just calling it the unit. Our unit of conductivity for water as a reference point is 0.6. And if we're dealing with computers, because that's specifically what it's about, in the 1990s, if you're old enough to remember ever doing this, some of you never touched this stuff, you put together a computer and you'd put something called a heatsink on the main processor. Whatever got hot, you put a heatsink on, usually with a little fan attached to it. And this would act like a little metal radiator, usually made of aluminum, sometimes coated with different coatings, sometimes having different metals, sometimes having all sorts of stuff going on. One of the ways to improve the conductivity, one of them, was to put on something called heat sink compound or thermal grease. Now it has a conductivity we're going to call 1. It's so close to being 1, we're going to call it the unit of conductivity. That's that old school 1990s, slightly upper grade thermal compound. Now one of the other ways to get the heat to transfer, oddly enough, was not to use this stuff, but to have the heat sink have a surface that matched really, really perfectly with the top of the chip. Because that wasn't the priority for some fucking reason when people made these, they'd get it as close as they could. The only way to get it better was to absolutely take the processor out, put it in a holder, and plane off the surface to where it was completely flat and completely smooth. Flat and smooth and level are not the same things. And then polish it to where it had a mirror finish to where it was one surface with the least amount of surface area. And then take our heat sink, which has the maximum surface area in those spines, the hedgehog thing on top, and on the underside where it was flat, make it really flat and press it against it. You didn't even need a thermal compound if you didn't want to, but you'd put it on anyway because it would make it to where stuff wouldn't get between the two layers, because the top of the chip was a lot of the time copper and the heat sink was a lot of time aluminum. Having them touch each other, they'd kind of chemically corrode with each other, but as long as they were electrically connected, because they would be by pressing them, they would mostly not corrode, and the heatsink compound could be put on as well. But that heatsink compound was white thermal compound, based on whatever was in it. Could have been platinum or lithium, doesn't matter. But it had a conductivity rating of 1 unit. 6 conductivity units, we're going to call them, is for silver thermal compound. Now all it means is it had some silver in it. Well, how conductive is silver by itself? Solid silver at room temperature is around 427 to 430 units of conductivity here. So it's not improving it much, but it does improve it from a value of 1 to 6. It's 6 times more conductive. The next one up is 13 units of conductivity. We're now 13 times as conductive in 1990, or the improved silver version of it, double or more. What is this stuff? Gallium. It's a liquid at almost room temperature. It's actually liquid at warm temperature metal. And what you do is you put it on the chip, on the top of it, just the top of it, and it would chemically bond itself aggressively sometimes to whatever that chip was covered with, like copper. It would wet the surface, acting like a room temperature liquid almost. Solder. We're going to get to that joke in a minute. And then we put on a heat sink, but it couldn't be aluminum. It could be copper, but it couldn't be aluminum, I guess. The aluminum will be attacked by gallium violently. You don't want to use that. But it would chemically bond them to each other almost, but not quite. But it would conduct heat much, much better than any of these. 13 times better than our baseline that we're calling our 1 unit of conductivity, 1990s thermal grease. Let's continue. What about tin? Tin is the primary element in solders. It has 62 units of conductivity. This would be hot solder. Now there's low temperature melt solders that are low enough that you can heat it up with a heat gun and basically solder the heatsink to the chip. Well, not to the chip. That would be the bare silicon. Most of them have a copper plate that's pressing right up against the silicon. Might have a little springy, spongy material to make sure it doesn't damage it. And that might make it less conductive. And yes, in the 1990s, we would have, in some cases, a bare actual silicon die sitting there waiting to be broken that we would press the heatsink against completely. We'd put little spongy, not electrically conductive material around it, and it would press into it. But it wouldn't break it, and you'd get really good contact. Some people even carefully polish the silicon down with diamond rouge and polish their heatsink down to where they could get a perfect connection and not even use any thermal compound. Thermal compound will work with silicon just fine. Even the liquid gallium stuff might work. But liquid gallium is electrically conductive. So is solder tin. But soldered tin can be made liquid and permanently bond it mechanically. That's a good or bad thing depending on whether or not you're going to ever have to remove it or it ever gets bumped even lightly. What's more conductive than tin? The aluminum. 200 units of conductivity. Solid aluminum. But it'll react to sometimes these thermal compounds and definitively will react to the liquid gallium alloy. What's more conductive than aluminum? And again, we're doing 200 times as conductive as the heatsink grease from the 1990s. Solid copper, again, is 390 units of conductivity here. That's very close to the 427 for silver. Much cheaper. And honestly, at 400 times almost of the conductivity thermally, that's fine. That's also very expensive, but not as expensive as silver. What about something exotic like graphene or graphite? 470 units. It's not that much of an improvement. We're getting diminishing returns for exoticness. And graphite's thermally conductive, but it's also electrically conductive. It also forms a resistor, which means it makes heat rather than just conducting electricity. It produces heat rather than a lot of other things. It also chemically will react more. What about superfluid liquid helium at ultra-low temperature? 100,000 units conductivity. Awesome. That's why you see it used for supercomputers, like the supposedly quantum computer that Google does. But that's because it has to be used at very low temperature in the first place, and it's under a certain pressure level or not. That's 100,000 units. Now, theoretically, we can do the same thing at room temperature with something that isn't a liquid. And again, if you pour a liquid over a hot object, it drags the heat away by heating up the water and then flushing the water away. Most of that liquid helium cooling is done by just moving the heat away. Water, well, we could use that. Water cooling on computers is pretty popular now too. But again, it's 0.6 units of conductivity, but it makes a good heat sink or thermal mass. Or does it? Now let's talk about what is used in laptops, and most of you have it in your computers. Heat pipes. They work at anywhere from 50,000 all the way down to 1,000 units of conductivity. They're really good happy medium, and they can be made very cheaply, but they can also conduct at 100,000 units of conductivity, hypothetically. It works out to 50,000. We have now a ridiculously not diminishing return here. Why? Because it's just copper tubing that's been welded shut at one end. Some websites and some videos keep saying soldered. It's welded shut, truly welded. And then it's evacuated for every gas possible. It might include a gas on purpose, but it evacuates it to lower the pressure, and they put in a couple of droplets of water before they do that. The water at lower pressure will evaporate rapidly. It'll go from a liquid to a vapor really easily, and then at the other end of the tube that's also now welded shut, it'll condense at the slightly cooler end and drag the heat very quickly from one end to the other, distributing the heat even faster than the copper tube that it's in by a factor of like 2 to 3 to 1. I mean, really, it's 3 or 4 to 1 actually. So, and it also lets you drag it to a thermal mass, being copper or whatever material you want to. I'll have a separate list for thermal mass ratings, but you get the idea. How good is copper versus aluminum versus water versus steel as a thermal mass to get the heat out? Heat sinks, I sometimes called them hedgehogs with spines on top of them. I used to make them by taking a mass of aluminum or copper and running a saw over it with a pole saw that would grind through and cut a pattern of XY cuts and then go through this way to where I had lots of really thin spines sticking out. I use a grinding disc. The other method was to get a piece of copper. This was easier. Chemically strip the surface of it and coat it with a layer of tinning flux and heat it up in an oven so it's covered with tin. And then put on tin-ended bits of wire stuck in on a board, pressing down on it, pushing the pins into the solder, and heat up the whole thing in an oven, pull it out, and have a big heat sink the size of the entire motherboard, and then use that for a heat sink with no fan. Just saying. So if you're wondering why we use copper or aluminum, but a lot of people like my age avoid the gallium alloy and would just rather take a grinder or a polisher to the heat sink and maybe even to the chip just to get this to work better, now you might understand. But yeah, heat pipes, the reason in your laptops, they work better. That's all. Now, I knew about this stuff, never did a video about it, but I didn't do a deep dive into why. And again, the heat pipes, they just have that fluid in it and a wicking material, like braided copper in them. Cheap. Thanks for watching. Have a good day. Good luck with that. I hope this has been useful to everyone watching.